Imagine a power source so dense that a pellet smaller than your fingertip can replace a ton of coal. This is the promise of nuclear energy. In today's journey, we'll witness how raw uranium evolves into reliable, carbon-free electricity. We'll go inside massive steel vessels, past glowing fuel rods, and into the heart of human ingenuity. Along the way, we'll confront the challenge of taming an unstoppable chain reaction. You'll see how each component, from silver zirconium tubes to silent robotic arms, works in harmony. By the end, you'll appreciate why 440 reactors quietly power 10% of our world's electricity. Unlike fossil fuels, nuclear reactors produce zero carbon emissions during operation. Deep inside the reactor core, heat is generated without a single molecule of carbon dioxide released. This clean process helps countries meet ambitious climate goals and reduces harmful air pollution. In many regions, nuclear plants run steadily day and night, providing a stable backbone for modern grids. As wind and solar ebb and flow, reactors keep voltage constant and frequencies stable. They pair perfectly with weather-dependent renewables, ensuring that cities never lose power. When you flip a switch at home, part of that light might owe its existence to a silent, smokeless nuclear guardian. Around 440 nuclear reactors operate worldwide, powering roughly 10% of global electricity demand. These plants span 5 continents, from the rolling plains of France to the coast of South Korea. Each reactor complex represents billions of dollars of engineering, training, and safety protocols. Together, they prevent the release of hundreds of millions of tons of CO2 every year, equivalent to taking tens of millions of cars off the road. Young engineers, scientists, and policymakers collaborate across borders to maintain and improve this fleet. Despite public misconceptions, nuclear technology has demonstrated an impressive safety record, refining designs with decades of lessons learned and rigorous international oversight. At the heart of every reactor lies uranium fuel pellets. Each pellet, barely larger than a fingertip, harbors astonishing energy potential. Crafted from refined uranium dioxide powder, these ceramic cylinders withstand extreme heat and radiation. Skilled technicians inspect each pellet to exacting standards, ensuring structural integrity. When millions of these tiny cylinders are arranged inside a reactor, they become the powerhouse of atomic fission. Their compact form factor simplifies handling but demands precise engineering and safety checks. It's this combination of small size and immense energy density that makes nuclear power uniquely capable of meeting large-scale electricity needs with minimal environmental footprint. Consider this. One uranium pellet holds the energy equivalent of 1 ton of coal or hundreds of gallons of oil. That single pellet can generate enough electricity to power a typical home for nearly a month. The difference in energy density explains why nuclear reactors occupy far less land than solar farms or wind arrays of equal output. Yet harnessing this density safely requires a delicate balance. Engineers design fuel assemblies to contain fission byproducts and channel intense heat to coolant systems. In the next scene, we'll see how these pellets are transformed into fuel rods and assembled into larger structures within the reactor core. Once pellets pass inspection, they glide into slender zirconium alloy tubes. Zirconium's low neutron absorption and high corrosion resistance make it ideal for handling radiation and hot water. Technicians stack pellets end to end inside each tube, creating a column of heat-producing fuel. Throughout this process, robotic loaders and precise automation ensure each rod seals perfectly to prevent leaks. These fuel rods become the basic building blocks of the reactor core. Their smooth surfaces and uniform dimensions guarantee even heat transfer. In the following sequence, multiple rods group together into assemblies that will one day sustain a controlled chain reaction. Over 200 fuel rods gather into a single fuel assembly, bound by sturdy grids and spacer springs. Engineer teams lift these assemblies crane by crane, inspecting welds and flow channels. Each assembly measures several meters long, yet fits perfectly into the core's lattice. This modular approach simplifies maintenance and fuel shuffling during routine refueling. It also allows operators to tailor reactor performance by adjusting the arrangement of assemblies. The core comes alive when dozens of these bundles lock into position inside the reactor vessel. But before we dive into that moment, let's examine the vessel that houses this extraordinary process. The reactor vessel is a mammoth steel cylinder with walls exceeding 20 centimeters in thickness. Crafted from high-strength steel alloys, it stands as the primary barrier between radioactive materials and the outside world. Its interior features heavy ceramic coatings and interior reflectors to aid neutron economy. Every weld undergoes ultrasonic and radiographic inspections to detect even the tiniest flaw. Surrounding the vessel is a thick concrete shield, attenuating stray radiation. This design legacy stems from lessons learned over half a century. Safe and reliable operation depends on the vessel's integrity, making it one of the most critical components of any nuclear installation. Next comes the critical moment of loading the core. Massive overhead cranes lift fuel assemblies above pools of borated water. Beneath the serene blue surface, robotic arms carefully guide each bundle into its designated hole in the reactor's lower core plate. The water serves both as a coolant and as a radiation shield, allowing workers to stand safely at control consoles. Sensors track alignment with millimeter precision, ensuring each assembly slides smoothly into place. This underwater ballet of steel and water is choreographed to perfection, balancing speed and caution. Only after every assembly is secure does the reactor move one step closer to startup. With fuel in place, the reactor is primed for fission. When it begins to produce power, you'll see a ghostly blue glow, Cherenkov radiation. This eerie luminescence occurs when charged particles exceed the speed of light in water. Although no particle can outpace light in a vacuum, the dense water slows light waves. Electrons breaking that local light barrier release photons in a mesmerizing blue flash. This signature glow is both beautiful and functional. It indicates active fission and helps operators visualize core behavior. Yet, despite its brilliance, the true magic lies in controlling the invisible chain reactions fueling this glow. Control rods are the reactor's steering wheel. Crafted from boron-infused alloys, They absorb neutrons randomly racing through the core. By inserting rods deeper, operators dampen the chain reaction. By withdrawing them, they allow neutrons to spark more fissions. Sophisticated drive mechanisms adjust rod positions with centimeter accuracy. During startup, control rods gradually lift, letting neutron population grow until the reactor reaches criticality. Automated safety systems constantly monitor reactor power and temperature. If any parameter drifts outside limits, rods automatically reinsert, halting the reaction. This interplay between neutron absorption and release defines how reactors maintain stable, controlled energy output. Once control rods lift, neutrons zip unabated between fuel rods. Some collide with uranium atoms, splitting them in two. This fission event releases energy as heat and propels 2 or 3 new neutrons. Each of those can split additional atoms in an exponential cascade. The reactor core becomes a dynamic network of collisions, producing gigawatts of thermal power. Operators fine-tune control rod positions, managing neutron flux and power distribution. This delicate balance ensures steady output, averting dangerous power surges. The chain reaction is the heart of nuclear energy, a testament to physics harnessed safely through meticulous engineering and rigorous operator training. At an atomic level, a neutron slams into uranium-235, deforming its nucleus. The nucleus stretches and splits, releasing energy stored in the binding forces. Fragments of krypton, barium, or iodine fly away, accompanied by kinetic energy and heat. 2 or 3 additional neutrons zoom out to continue the process. This dramatic release of energy, millions of electron volts per fission, translates into the thermal energy that drives our turbines. Modern reactors optimize fuel geometry and moderator composition to maximize efficiency and extend fuel life. Each step in this microscopic ballet is governed by precise physics and decades of research. Every fission event generates roughly 200 million electron volts of energy, converted into heat as fragments decelerate in water. Meanwhile, prompt neutrons maintain the reaction, while delayed neutrons provide a crucial safety margin. Engineers rely on delayed neutrons to monitor and control the reaction's pace. They allow for slower adjustments, preventing runaway scenarios. This fraction of neutrons, just a few percent, makes the difference between manageable power and irreversible escalation. Reactor control systems use feedback from neutron detectors and temperature sensors to adjust rod positions in real time, forging a stable equilibrium between heat production and removal. As neutrons multiply, the chain reaction builds momentum. In mere seconds, power jumps from a few kilowatts during tests to hundreds of megawatts at full operation. The core temperature climbs rapidly until stabilized by coolant flow and control rods. Engineers monitor each surge through computerized dashboards, ready to intercede if fluctuations arise. Safety injectors stand on standby, capable of flooding the core with borated water to absorb excess neutrons instantly. This layered defense ensures no single failure can trigger a catastrophic event. The choreography between physics, hardware, and human oversight safeguards every moment of reactor life. Circulating water serves as both coolant and moderator. As neutrons slow down in water, they become more likely to induce fission. High-pressure pumps drive water through the reactor, keeping it from boiling at temperatures above 300 degrees Celsius. Under this immense pressure, water absorbs immense heat while retaining its liquid state. Special piping and heat exchangers channel this hot coolant to the steam generator. Throughout the circuit, sensors track flow rate, temperature, and pressure. Any deviation triggers alarms and automatic protective actions. The reactor's lifeblood is this controlled flow of water, seamlessly transferring energy from fuel to power plant. In the steam generator, superheated primary coolant passes through thousands of helical tubes. On the shell side, secondary water turns to steam without mixing with radioactive fluid. This separation ensures that turbine equipment remains free of contamination. Steam purity is paramount for turbine longevity, so purification systems scrub out impurities before the generator stage. Operators adjust steam temperature and pressure to optimize turbine efficiency, typically around 550 degrees Celsius and 16 megapascals. The art of heat exchange is central to reactor performance, balancing maximum thermal output with minimal maintenance and operational risk. High-pressure steam races into turbine blades, causing them to spin at thousands of revolutions per minute. Each blade arrangement is aerodynamic, extracting maximum energy from steam flow. As the rotor accelerates, it powers a massive generator, converting mechanical motion into electrical current through electromagnetic induction. Turbine halls are immense spaces filled with precision machinery and echoing with the hum of rotating shafts. Engineers observe vibration monitors and temperature gauges to ensure everything turns smoothly. Any imbalance could stress bearings or damage components. But when run correctly, turbines deliver continuous, reliable electricity for years with minimal downtime. Connected directly to the turbine shaft, the generator houses coils of copper wire in a potent magnetic field. As these coils spin, electrons flow, creating alternating current at grid frequency. Step-up transformers boost voltage for efficient long-distance transmission. This electricity travels across high-voltage lines, delivering power to homes, hospitals, and industries. On-site switchyards and circuit breakers manage load distribution and isolate faults. Grid operators coordinate reactor output with other power sources to maintain stability. Nuclear plants excel at providing base load power, ensuring consistent delivery of large-scale energy day and night, rain or shine. After steam leaves the turbine, it condenses back into water in the condenser, cooling in vast basins or cooling towers. In natural draft towers, warm water cascades over hot fill, releasing heat as water vapor columns visible for miles. Cooling towers thus serve as the power plant's final heat rejection system. They require minimal chemical additives, relying largely on evaporation and airflow. Environmental controls monitor thermal discharge to protect aquatic ecosystems. In some modern designs, Air-cooled condensers eliminate water consumption entirely. Regardless of the method, heat must be dissipated to complete the cycle, keeping the reactor primed for continuous power production. Encasing the reactor is the containment building, a fortress of reinforced concrete over a meter thick. Designed to withstand earthquakes, hurricanes, and even airplane impacts, it forms the last line of defense. Inside, the steel-lined pressure suppression pool and safety relief valves manage excess pressure in emergencies. Advanced designs include filtered vent systems to capture airborne radioactivity before release. Periodic integrity tests ensure no cracks have formed. This barrier protects the public and environment, embodying decades of safety culture. Its very existence speaks to the value placed on preventing radiation exposure under all conceivable scenarios. Every aspect of a reactor's safety system stems from lessons learned in past events. Seismic sensors can trigger automatic reactor shutdowns if tremors exceed thresholds. Backup diesel generators and battery banks guarantee power for cooling pumps during grid failures. Passive safety systems leverage gravity and natural circulation to cool the core without external power. Fire-resistant cables, redundant control rooms, and multiple physical separation lines further isolate critical functions. Regulators enforce stringent testing and emergency drills. This multi-layered defense-in-depth approach ensures that even if one barrier fails, several more stand ready to stop a chain of failures from endangering people or environment. Over time, fuel assemblies lose efficiency and must be replaced. After removal, they cool in deep pools of borated water for years. These pools provide both radiation shielding and heat removal. After sufficient decay, some fuel may be reprocessed to extract unused uranium or plutonium. Other assemblies transferred to dry cask storage, massive steel and concrete cylinders designed for long-term containment. Storage sites are engineered for seismic stability, temperature control, and radiation monitoring. While spent fuel remains hazardous for thousands of years, current strategies ensure safe management and minimal environmental impact, reflecting the nuclear industry's commitment to stewardship across generations. Each large reactor can supply enough electricity for 1 million people, powering homes, hospitals, schools, and businesses. That single core fuels high-resolution screens, life-saving equipment, and critical infrastructure. In regions with limited resources, nuclear plants offer a stable foundation for development and electrification. Through cogeneration, reactors can also provide district heating or industrial process heat, maximizing utility. Local communities often benefit from job creation and economic growth surrounding nuclear facilities. Public outreach programs invite citizens to learn about plant operations and safety measures, fostering transparency and trust. In our global quest for sustainable energy, nuclear remains a cornerstone. Small modular reactors are poised to reshape nuclear energy's trajectory. Factory-built modules cut construction times and costs dramatically. Their compact footprints allow deployment in remote areas or existing power sites. SMRs under development often integrate passive safety features that require no operator intervention or external power to remain safe. With capacities from tens to a few hundred megawatts, they serve as perfect complements to renewables, filling gaps in baseload power. Recent milestones, such as the U.S. permit for TerraPower's sodium-cooled design and Amazon's plan for 12 module installations by 2030, underscore growing momentum. The future looks modular and more adaptable than ever. Nuclear energy splits atoms to light the world, combining physics, engineering, and human ingenuity in one elegant system. From tiny uranium pellets to massive turbine hulls, every step demonstrates our capacity to harness nature responsibly. In the face of climate change and rising energy demand, nuclear power offers a proven path to large-scale, carbon-free electricity. By understanding its inner workings and robust safety culture, we foster trust and inspire innovation. The next time you flip a switch, remember the chain reactions humbly hidden beneath reinforced steel and concrete. Explore how cutting-edge nuclear technology is shaping a sustainable and energy-rich future.